Hi, everyone. So just as these AI-generated street racers push their cars to the limit, AI workloads today push the limits of scale and speed. Dense fog can impair a driver's vision and cause them to slow down. Lack of fine-grained visibility at the QPair level causes AI workloads to slow down. And AI teams to slow down when diagnosing connectivity issues, not only at pre-race time, during GPU cluster onboarding, but also at race time for the workloads at runtime. Debris on a track can puncture a tire and cause a crash. And just like that, NIC and link flapping causes AI jobs to crash as early as within the first hour of a GPU cluster. So I'm Lerna Ekmekcioglu. I'm a solutions engineer at Clockwork Systems. Before this, I was at AWS for 3 years. And before that, I was in large financial services firms for 17 years, worked as an infra engineer. Back then, that's what we called it. And I worked on things like centralized authentication systems for all applications in the firm, low latency monitoring for all servers in the firm. So you needed highly scalable, highly available, highly resilient solutions for those problems of scale. And that's what I enjoy doing. So today I'll be talking about AI/ML networking challenges. I'll show some demos and also go over learnings from a solution so that our AI workloads can run at full speed, just like these racers' cars. So first up is quick recap of AI workload layers. On top, we have the job itself, which is the workload, which is just an LLM model in my case. And it is built using libraries and frameworks such as DeepSpeed and PyTorch. And if you have a large-scale job, then you need the inter-GPU communication. For that, you use collective communications libraries like the one from NVIDIA called Nickel. And at the bottom, you have the network device. And it has to be RDMA capable. And RDMA, it actually enables fast data transfers. And you can go from one node to a remote node's memory over the fabric bypassing the kernel. That's how you get the fast data transfer. And the fabrics themselves, they provide high throughput and low latency. Here, RoCE v2 and InfiniBand, they are the top two. They differ at network and link layers. InfiniBand relies on proprietary protocols and proprietary hardware. It performs really well, but it can get costly. RoCE v2 relies on standard protocols that we already know, UDP, IP, and Ethernet, and needs standard hardware. It performs comparably well as InfiniBand, and it is less costly because these are probably hardware that you already have laying around in your data center. So what are the demands of the AI workloads from their networks? So first I want to take a step back and take a look at traditional networks that we're used to. And those are, to me, like busy streets in a big city, like New York, where we are from. And AI networks, they're like a high-speed racetrack. So in a traditional network, you expect delays, there's going to be packet drops, and you expect best effort service. In AI networks, those are designed for lossless transmissions, so you get minimal delays and best performance. Traditional networks, network card speeds are 25 gigabits per second, and you have a safe link utilization rate that is 50% or below, because you don't want too much congestion in those pipes, then you get more packet drops, more delays. AI networks go anywhere from 100 to 800 gigabits per second, and the link utilization reaches 95% or more, because these workloads are running all the time. Traditional networks, you get heterogeneous workloads, and the speed of one application doesn't directly affect the speed of another app. And AI networks, you have homogeneous workloads that are highly correlated. So if you were to profile one of these workloads, like an LLM training job, then you see that it consists of cycles of compute followed by communicate. And if you look at the overall job completion time, 30% or more of that is spent on networking. Somewhere in there is that animation. So here is an all-Redis collective, and components of the sum goes around the ring, and total sum is computed, and then it goes around the ring one more time, so that each and every worker node has the total sum. So the finish time of this operation is based on the sum of the latencies within the ring. And this is just like a pit stop to me. So in the pit stop, pit crew is not done until each and every team member is done. Similarly, GPUs are not going to proceed to the next step until each GPU synchronizes their partial results, like partial gradients. And the slowest team member is going to determine the team speed. So slowest flows or nodes, in the case of GPUs, are going to determine the job throughput. So what's happening under the hood at the collective communications library that enables this inter-GPU communication? So here I have 2 nodes, 8 GPUs, 16 network cards, a sender and a receiver. GPUs, they're generating messages that get split into chunks that get mapped to Q pairs. Q pairs are just like sockets. And then the network card takes that, packetizes it over the fabric, and then receiving NIC takes it and takes it up in the reverse order to the receiving node. Topologies that we may see here can be rail optimized, such as the ones that have the top-of-rack switches and the nodes themselves. And then if you have large enough clusters, then you may get also spine layer switches and core layer switches. That's like a FAT3 network, basically. So we speak to GPU cloud operators and AI workload owners, and these are the challenges that we hear in the field for AI workloads and AI networks. Lack of visibility, lack of reliability, lack of predictable performance. So first is lack of visibility, and this is an actual alert that one of these teams has received. Top-of-rack switch has 3 down uplinks, and this has happened 6 months ago, but they only figured out now. And this is happening because teams are missing real-time insights into the connectivity between the nodes in the cluster, the quality of the paths. They only get aggregate level metrics like network card counters or switch counters, but they don't get fine-grained visibility down to the Q pair level. And when this happens, okay, let's go back to that. Maybe we're not going to get that one, huh? Okay. When this happens, basically it causes them, it slows them down when diagnosing connectivity issues, not only at the GPU cluster level, when they are first onboarding these GPU clusters, they're UAT testing, performance testing the GPU clusters, right, before starting to run those AI workloads. And also at the workload level, when they're running their workloads at runtime, they don't have this level of visibility. So at Clockwork, basically, this is our foundational research. It's a paper, Usenix paper, out of Stanford University. The paper has a lot of details. It's software-based clock synchronization. It's high precision at scale, and it measures one-way delays highly accurately. Okay, I think I know what's going on now. All right, it's okay. So I'm gonna summarize this paper very quickly. Basically, it is based on a probe mesh, and it's a lightweight probe mesh. There's probes in between each of these, kind of maybe from 1 node to 5 other nodes, and the probes go through machine learning for high precision offset and drift measurements. And then when you have many subloops within this graph. So what you do is kind of like triangulation for your location. You leverage subloops within the graph and take advantage of the fact that clock sync is transitive. And that way you can use going around subloops. You can calculate the edge errors to reduce errors based on path asymmetries. And then you can measure one-way delays accurately. So first here I have 4 nodes. 2 nodes are in one rack, 2 nodes are in an adjacent rack. Each node has 8 GPUs and 16 network cards. And the network cards are marked as healthy because I can see probe traffic going through them. One-way delays within the same rack between these 2 network cards that have their clocks synchronized. They are in the hundreds of nanoseconds range, like 500, 600 nanoseconds per Q pair. And if I look at one-way delays between 2 network cards across racks, it's at 1.5 microsecond range. So right now I don't have a workload running. What I'm going to do is I'm going to start a workload, and it's going to be a standard all-reduced job. And it started running between nodes 4 and 6. So we should see the throughput go up for nodes 4 and 6 in a second. Each of these network cards are 100 gigabits per second. I have 16 of them, so I'm reaching about 1.47 terabits per second, which is pretty good for this cluster. At the network card level, I'm getting about 91 to 92 gigabits per second, which is again pretty good for the max throughput I can get per network card. And now I should see also a difference in the one-way delays without the workload 1.8, with the workload anywhere from 3.1 to 3.4 microsecond range per queue pair. So each of these queue pairs are doing a little different in terms of the one-way delays. Next issue is lack of reliability. And in this case, the links have flapped more than 10 times over the past hour, and they need to send technicians to the data center to swap out cables. This is common in large enough clusters, according to semi-analysis, which is a well-respected AI publication. It can happen because you have large enough number of optical transceivers, and they tend to overheat or get affected by dust particles in the data center. So what happens is the jobs crash, which forces you to restart from your previous checkpoint. And typically what we see is AI teams, they take their checkpoints like at best every 30 minutes because checkpointing is also expensive. And what ends up happening is you're losing training time. I think that is the biggest pain point. As a result of that, obviously, I think you're also losing money. Somebody cares about that. Probably we don't, but they, finance or something. So the links can flap at an interior link from top-of-rack switch to a spine layer switch, or it can happen at the edge layer link from the node to the top-of-rack. And if that happens, like for rail-optimized design, then it is, more drastic. So I'm going to demo NIC flapping next. So first, I have the job already running in this cluster, the same all-reduced job. What I'm going to do is I'm going to flap a single NIC out of the 16 in node 4. So the first thing that we notice is that the job got grayed out. And you can see that the throughput for the job went down, so the job actually crashed. And the network card is marked as unhealthy since I brought it down. And we can see also all the network cards are no longer carrying any more workload traffic. So truly, this job crashed. And next, just to prove the point that even if I bring back this network card, the network card is going to come back. And here it is, healthy. But the job doesn't come back. Right? The job remains dead. So this is the point where I would fall back to my previous checkpoint if I took one. Some teams apparently don't even take checkpoints, so this is pretty upsetting if you had like weeks and weeks worth of training and then you didn't take a checkpoint. And just to prove the point that I'm not lying, that the network card is truly back. I know it's because the probe traffic is back. Per queue pair, I can see probes going. I can see when the card was down. And now it's back, but the workload didn't come back. So next is 3 runs on Oracle Cloud. The first run is in a similar cluster, 100 gigabits per second, 16 network cards, so I'm reaching 1.5 terabits per second, similar to the demo, steady state. The next run is actual failure state, which is what we saw in the demo. So the NIC flaps, the job dies, the NIC revives, the job stays dead. This is what's happening in the clusters today. And the last one is about a solution that provides auto-recovery. So what happens here is the NIC flaps, and you can see a slight degradation in throughput. And this is happening because you lost 1 network card out of the 16, so the remaining 15 network cards are doing double duty. And that's why we have degraded in throughput a little bit, but once we revive back the network card, then all the network cards are doing normal duty, so we're back to original throughput. And the idea here, I think the learnings from this is that there's a choice in when and if to fix the flap NIC, And one idea is, why not run until the next scheduled checkpoint like this in the degraded throughput, and then fix the NIC, and then come back to the original throughput so that you can minimize downtime as much as possible. Now, the last one is lack of predictable performance, and the application is slow, flows are contending for bandwidth, and you get, as a result, low throughput and high latency. So here, basically, the queue pairs are colliding at the spine layer flows, and the sources are not aware of which paths are more or less congested, so they're putting the same amount of data on each path, and some queue pairs are doing worse than the others. So here I have, again, 3 runs on an ECMP testbed. I have an all-to-all job. Max throughput I can get should be closer to 100 gig, but on top you're seeing 84 gigabits per second. And you can see below, one-way delays for some of these queue pairs are at 50 microsecond range, and those slowest teammates are taking down the team speed. Slowest queue pairs are taking down the job throughput. If I introduce a second all-to-all job, then I'm getting 50% or less throughput that I could have gotten in this test bed. And that's because there's a lot of contention now in the fabric. You see queue pairs with one-way delays reaching 100 to 150 microsecond range. And the last one is basically about a solution where you're balancing the load of the data that you put on the queue pairs such that you basically reduce the one-way delays as much as possible by shifting the bytes from congested to less congested paths, like a good traffic cop, and you increase the throughput for these 2 jobs to closer to the max you could get. So now you're getting 92 gigabits per second in the same test bed. So finally, the key takeaways are, if we have fine-grained visibility down to the queue pair level, that helps us not only speed up the diagnosis, but also resolve connectivity issues, whether at fleet level, at the network level, but also for our workloads at runtime. NIC and link flapping is a real issue that happens in large enough clusters, so we want a checkpoint according to our business requirements for what that workload needs so that we can recover from them without breaching any SLOs and without losing any of our hair because we lost training time. And delays in those slow queue pairs, they impact overall job throughput. So if you see any issues with job throughput, this is a good area to explore. And finally, a couple of predictions. Training and inference workloads we're seeing right now, they are actually merging into the same AI network, and storage workloads are also joining them thanks to the benefits of RDMA. So we used to see partition and bespoke AI networks per AI workload function, and that's going away, and we're going to get more and more of the unified AI networks. And finally, the road ahead, it's looking like, basically, we really do care about efficiency here. It's not just speed and scale. It used to be that things are more monolithic, but now that is giving way to heterogeneous environments. So we'll get more and more cross-vendor, mixed-generation GPUs. It's too expensive to be tossing away your previous generation GPUs just because a new one came along. And we're seeing more and more of the mixed network card suites. And finally, within this context that's constantly evolving and changing, we believe the software-defined approaches are going to adapt faster to provide visibility, reliability, and performance so that our AI workloads run at top speed. Thank you, and here you can find the Usenix paper and more. Thanks.